Okay, once again, we have the same situation as before, transformation, where A is an M bind real matrix defining the transformation. So that this space is your space V equals Rn. Over here we have the space W equals Rm, and every vector in V will go into some vector in W. Now, there certainly are vectors in W that are not images of any vector in V, and that's going to kind of be key. So we have Rm. Now, we know that the row space of V goes to a column space over here in Rm, column space of A, which is the row space of A transpose, but I'm going to call it C. Okay? And I'm going to depict that column space and the null space of Rm, not by rectangles this time, but by straight lines, because the vector relationships will be clearer. So make sure I'm drawing this picture the way I want to. I've drawn the picture. If I don't draw it the right way, the arrows are not going to work. And that's the complicated thing that I needed to work out. Okay, so this is C. So every vector in the row space, and in fact every vector in Rn, will map to some vector on the space C. And then I'm going to depict the null space of A transpose, but I'm just going to write it as N. This is the null space over here in Rm. So here's Rm. Here's your null space. Here's your column space. Null space of A transpose. I guess I better write that down. Here's your null space of A transpose. Here's your column space, which is the row space of A transpose. Column space of this matrix is the row space of its transpose. Okay, so we've got a series of vectors here. So let's just say that this vector maps over here to what? Well, it maps over to some vector in the column space. Okay, this vector will map to some other vector in the column space, and I'm looking at my picture so I don't get these arrows crossed with one another. And that isn't where I really wanted that one to go, but it's going to be okay. So I'm going to map this vector over to here, and I'm going to map this vector, let's say, to here. So that these three vectors map to these three vectors over in the column space. And if I want, I can call this V1, call this V2, call this V3. So that I'll call this one W1, I'll call this one W3. Now my labeling is going to get messed up if I'm not careful. Call this one W2. Now let's suppose that there's some vector B over here in the space W. And that vector is not in the column space, but it's not in the null space of A transpose either. Okay, it's a sum of some vector in the column space and some vector in the null space, and it's a unique sum because this is a direct sum. I'm not going to belabor that idea, but let's just say that B is here. Yeah, I'm going to change that. I want B to be a little bit shorter. I'm going to make B here. So I'll erase that and hope that doesn't mess up my picture. Okay, so there's my vector B. That's kind of a target vector, and what I'm wanting to do is find a vector in the vector in Rn that comes as close as possible to the vector B. Okay, I really don't like that, but Well, okay, what is W1? Well, W1 could be depicted by this. So here's my W1. And my W2 and W3, using different colors. Okay, W3 might be this vector, and W2 might be represented by this vector. Now, which one of these three vectors is closest to the vector B? Well, here's how far this vector is from B. Okay. Used the wrong color, so I'm going to hopefully. Okay. And W2 is this far from B, and W1 is this far from B. Well, it's pretty clear that by this picture, W1 is closer to B than either W2 or W3. Now, I'm going to redraw these axes down here because things are a little cluttered up. And incidentally, this picture would be accurate if this was R2. So you can even think of this for the moment as being R2 with one axis representing the column space, the other axis representing the null space of A transpose. Now, in general, these are really going to be planes or hyperplanes, are going to be higher dimensional spaces, but everything that we do here can formally be shown to work. Okay, so what do we do here? Well, we draw our vector B again, wherever it might happen to occur. And how is it that we're going to find the vector in our column space that's as close as possible to the vector B? Well, it should be obvious. If what we're going to do is we're going to project B onto the column space. In other words, the vector that we're looking for is the vector whose projection onto the column space well, it is the vector projection of B onto the column space. Okay, so this is the W it's the W that's closest to B. Well, that W is in the column space, so that W came from some vector over here in the Rn. And it had to come from a vector, well, okay, it came from some place in Rn. Okay, now it might have come from several places in Rn, but came from some X in Rn. We want to find that X.